Well, welcome back. In this video we're going to move on to the next discovery and person of discovery. Ernest Rutherford is absolutely one of the most brilliant physicists slash chemists slash scientists in general that we've ever known. He did a lot of work in the early 20th century to help us develop a better understanding of not just the atom but the process of radioactivity. His discoveries led to the nucleus, eventually the neutron. It was just an amazing academic life. So for us, we're studying Ernest Rutherford because he gave us a new model of the atom that improved on Thomson's plum pudding, because he ran one of the most famous experiments in science history. And the name of that experiment was called the gold foil experiment. And this video here will take you a little bit through that experiment, so I invite you to hit pause and take a moment to watch this one, linked in your assignment. But basically what he was doing was following up on some of his research into the alpha and the beta particles. Specifically in the gold foil experiment, Rutherford was working with the alpha particles. And he knew what alpha particles were by this time. He knew that they were the helium nucleus. They were positive 2 charged. He knew they were fairly massive, kind of weakish. They would pass through some things, but the thicker the object they tried to pass through, they would be stopped. So kind of a weakish penetrating power. But the most important thing he knew was that they were positively charged and kind of weak. So in this experiment, he wanted to see how the alpha particles would react by passing through a very thin gold foil. Part of this experiment would tell Rutherford if Thomson's model of the atom was correct. Remember, Thomson's plum pudding model proposed that the atom was just a diffuse positive cloud, so something kind of insubstantial, where the little tiny electrons, real tiny, and not much mass, were kind of spread out through there. Well, if that was the case, then this alpha particle should just tear right through the gold foil, very thin gold foil, and pass straight on to the other side. So in the bottom of your screen here, you can see sort of the apparatus illustrated here or animated here. You've got a source of alpha particles and it's shooting toward this gold foil, and as expected, most of them did pass through, and that's very important. They did pass directly through, and they made little dots on this phosphorescent screen here, or it says here fluorescent, and so it would just kind of glow. When an alpha particle hit, you see a little glow dot on the screen. Well, they expected this to happen forever, with no exception. But lo and behold, as they let this experiment run, they started seeing some surprising results. They started seeing some slight deviations from straight through, and then some little larger deviations, and then some very big deviations from going straight through. And then there were some really surprising results. Some went virtually sideways, and some even bounced backwards. Every once in a while, one would bounce directly back at 180 degrees to its original path. And Rutherford famously said that was as surprising as firing a shell at a piece of tissue paper and having it bounce off and come back and hit you. That wasn't what he expected. Now, why did he choose gold? You may think that's an important part of this experiment. Kind of. Remember, he wanted something really thin. He knew alpha particles would be stopped by most anything, like a sheet of paper will stop really alpha particles. But gold is the most malleable of all the metals. You can make gold thinner than any other metal. And so it's also a large atom. So there's a lot of empty space in a lattice of gold. There's lots of little nuclei. I didn't know this at the time, but there's lots of little nuclei in there. And we will soon learn too that the atom is mostly empty space. And there's a lot of space between the atoms because they're so big. So that was his choice for making gold. Now, what do we get out of this experiment? He expected most of the particles to pass through the gold. They did, straight through. He saw a few or several be deflected at small angles, a smaller number be deflected at large angles, like sideways, and then an even lower number get shot straight back or sent straight back. So from that, Rutherford concluded that the alpha particles are hitting something. They're being affected in their flight by something. So the first thing he tried to figure out was why is he seeing small deviations, just slight movement from straight through? And that one could be explained by whatever the alpha particle was coming close to, not necessarily hitting, but coming close to, it was being repelled. So he said that whatever it's interacting with has a positive charge because it's deflecting it. And it's also not sticking, it's making it through. If it was hitting something negative, then there would be a coming together between those two objects. The alpha particles would just neutralize whatever they were interacting with. But it didn't. It passed through, but being pushed away in a repulsion. He also knew that it happened very rarely. Very few of the particles bounced off sideways, even less backwards. Not very many slightly. So he knew that whatever it was interacting with was small, and the chances of it happening were small. And then thirdly, he said, okay, well, whatever this is hitting is pretty dense. It's really pretty massive. Otherwise, these alpha particles would just blow it up like throwing a bowling ball at bowling pins. It would just knock it to pieces and scramble it. But it didn't happen. Whatever it was hitting was so dense that the alpha particle could be deflected or reflected straight backwards with no change to the gold foil. So that led Rutherford to say, we found this small, dense, positive thing in the atom. We're going to call it the nucleus, and he envisioned it being sort of the center of the atom. And he said, okay, well, if we have this small, dense, positive center, and we know we have electrons in there, they can't be interacting like smashing into each other, or else they would neutralize their electrical charge. So he said, okay, the electrons must be moving around that central nucleus far enough away so they don't come smashing into each other, kind of like the planets orbit the sun. And so that led him to say that the atom is mostly empty space. So we have a new model from Rutherford. We call it the nuclear model. Some people call it the planetary model. But it basically says there's a nucleus in the middle of the atoms. It's small, dense, positive, and the electrons are orbiting this nucleus like a planet orbits the sun. And so that's Rutherford's model. It's another big leap. It kicked the plum pudding model out in just a few years. It didn't last very long at all. So now, after this video, we're going to get back into Bohr and figure out what to do with all those electrons. Maybe Rutherford oversimplified the electrons just a bit.